And now it's time for another exciting math lesson, this time about the quadratic formula. Okay, that was pretty cheesy, I admit, but hey, we got to do some things to have a little bit of fun around here, okay? So for me right now, that's about as good as it's going to get. So we are going to be talking about lesson 4.4 today, the quadratic formula. So what are we going to learn? We're going to learn a couple of things. Number one, we're going to learn how to use the quadratic formula to solve quadratic equations. And then number two, we're going to learn about the discriminant and how to use this value called the discriminant to help us figure out what type of answers we can expect in terms of how many roots a quadratic equation will have, a quadratic function might have, and what type they're going to be. Okay, so that's what we're going to be talking about today. So over the course of the last several weeks, we've been learning different ways to solve quadratic equations. We started off by graphing them, and then we were making tables. We factored them into binomials. We used square roots. We learned about completing the square and the 6-step process. And so now we are going to add another method, another tool to our tool belt, to our toolbox that we can use to help us solve these quadratic equations, and it is the quadratic formula. Now, I know that many of you have used the quadratic formula in the past, so you're already familiar with it, and that's great. If you already know how to use the quadratic formula, you're already familiar with the formula itself. Maybe you learned a little song to help you memorize the quadratic formula at some point. That's wonderful, because we are going to be using the quadratic formula a lot, and you do need to know it. You need to have it memorized. So if you already have that memorized, or you're kind of there, that's a good thing. You're well on your way. So we use the quadratic formula when quadratic equations are written in standard form. So that's really the way we're going to apply it. We always put the equation in standard form, ax squared plus bx plus c, and then we apply the quadratic formula. So y'all are familiar with the quadratic formula. It is, of course, this right here. I want you to take a moment. I want you to write it down. Okay, I'm gonna just go ahead and pause the video while you write this down. And then once you've got it written down, come back to me. Okay, so hopefully you have it in your notes. Remember that the quadratic equation that you're working with has to be in standard form, ax squared plus bx plus c. And those coefficients, the a and the b, along with the constant c, those are the a, the b's, and the c that go into the formula. So you need to memorize this formula. The opposite of b, plus or minus the square root of b squared minus 4ac all over or divided by 2a. Okay, so you need to know this. You'll notice I said the opposite of b. A lot of people will say negative b. The reason I use the word opposite is to remind us that, hey, I need to change the sign of whatever b is. B may already be a negative number in this particular equation that I'm working with. And then if I say negative b, but then b was already negative, that can lead to some confusion. So that's why I always say the opposite of b. Folks, you need to know this thing. You need to know it. You need to know it really well. In fact, I would learn to be able to rattle it off just as quickly as you can. The opposite of b plus or minus square root of b squared minus 4ac all over 2a. Okay, if you can do it as fast as me, you got it down. So I'm going to be, feel free to stop by my door anytime and challenge me to a opposite of b plus or minus square root of b squared minus 4ac all over 2a contest. I would love to do that with you. It'd be a lot of fun. All right, so we got to know how to use the quadratic formula. I want to walk you through some examples here today for using the quadratic formula. Okay, here's the first one. So I got this function, f of x equals x squared plus 3x minus 7. So the first thing I ask myself is this in standard form? So I got x squared, ax squared, I got 3x, bx, I got minus 7, I got my c. So it looks good. It's in function form, so I'm going to rewrite it as an equation and set it equal to 0. So now I got my equation, x squared plus 3x minus 7 equals 0. Okay. My a value right here, the coefficient of the x squared, is a 1. My b value, in the blue there, is the 3. And my c value is -7. I want to make sure we get our positive and negatives correct on these. Okay, so I've got my A, and if I were you, I would just get in the habit. I don't have it on the slide, but I would get in the habit when I'm doing this, so you're really comfortable. I would just put A right over off to the side. A equals 1, B equals 3, C equals -7. Then when you go to the quadratic formula, the opposite of B plus or minus square root of B squared minus 4AC all over 2A. When you go to the quadratic formula and you plug in that A, B, and C, then you can look at it, you can see it. It helps you from making little errors of just, hey, I wrote down the wrong number. Oh man, I knew how to do this, Mr. Owens. I just wrote down the wrong number. I know my answer's wrong. It's just because I copied in the wrong number. Well, we got to avoid that. We got to plan against that. And one of the ways is by doing A equals, B equals, and C equals on my paper so that I can see them as I plug them in. Okay. So that's exactly what we're going to do too. Take the quadratic formula. I'm going to plug in the 1 where the A goes, where the A's are. So those are both going to be 1. I'm going to substitute in 1. I'm going to put the +3 in right here and right here. And so, the opposite of +3 is going to be -3, which is why I like to use the word opposite. 3, of course, is going to get squared. And, the order of operations, I'm going to square before I subtract. So the 3 is going to get squared. So it's going to make my 9. And then the -7 is going to go in here. So keep in mind, -4 times A times C, these are being multiplied, and 2 negatives is going to make this end up being a positive. And of course, 4 times 1 is 4, and 7 times 4 is 28. So this is going to end up becoming a positive 28. And then, I got the 9 squared, and then I'm going to be adding that. And of course, down here, 2 times 1 is still 2. So I can plug in those numbers. And we've already kind of talked through the arithmetic, and I've got my opposite of 3, my -3. I've got my 9 plus 28. So I take the 37 there, and then I ask myself, hey, is 37 a perfect square? No, it's not a perfect square. Does it have any perfect square factors that I could simplify that down? No, it does not. So it is in its simplest form. And that's my answer. And that's a perfectly fine way to write the answer. -3. And of course, keep in mind, this is 2 solutions. This has 2 roots, this quadratic. -3 plus the square root of 37, all divided by 2. And -3 minus the square root of 37, all divided by 2. Okay, so found my 2 answers. There they are. Let's do another one together. So this one, f of x equals 2x squared minus 16x plus 27. I look at this and I go, okay, it is in standard form. So I'm going to take it out of function form, f of x. I'm going to put it in equation form, set it equal to 0. And again, off to the side. I know I don't have it on the slide, but if I was doing this in class, I'd be writing this on the board. A equals 2, B equals -16, and C equals 27. So go ahead and write those 3 down. And now I'm ready for the quadratic formula. Oh, gee, I wonder if I could remember what the quadratic formula is. The opposite of B plus or minus square root of B squared minus 4AC all over 2A. I can remember. And you are too. Okay, so we take that equation, we jot it down, we start plugging in our parts. The -16 is our B value, +2 is our A value, +27 is our C value. So I'm going to substitute in those values, and then I'm going to crunch some numbers. -16 squared, that's going to be a +256. 4 times 2, of course, is 8. 8 times 27 is 216. And of course, down here, 2 times 2 is 4. And hey, here's the opposite of -16. Well, I know the opposite of -16 is +16, so that's pretty easy to do. So I get my +16, there's that 256, there's that 8 times 27, which is 216. Subtract those 2, and it is 40. Now at this point, on the last question, we stopped because there was no more simplifying that we could do. But there is a little bit more simplifying we can do here. I'm going to recognize that these 2 numbers, this numerator and this denominator, are both multiples of, they're both multiples of 2, but 16 is also a multiple of 4. So there can be some reducing going on there. And I know that while 40 is not a perfect square, it does have a perfect square factor of 4, because 4 times 10 is 40, and 4 is a perfect square. The square root of 4 is 2. So I'm going to simplify this on down. Okay, so negative 40, I'm sorry, the square root of 40, not negative 40, didn't mean to confuse you. The square root of 40 becomes the square root of 4 times the square root of 10. And of course, the square root of 4 is 2. So this becomes 2 root 10. So the square root of 40 becomes 2 times the square root of 10. And now I can simplify. Remember that when you have this plus or minus, it's really just, these are two different fractions that have common denominators. 16 over 4 plus 2 root 10 over 4. And 16 minus 16 over 4 minus 2 root 10 over 4. So these are just two fractions. Well, 16 divided by 4, of course, is 4. And 2 goes into 4 2 times. 2 over 4 is 1/2. And so we see that I'm able to simplify it down to 4 plus or minus the square root of 10 over 2. So we always want to put things in the simplest form. Now, students often ask, well, Mr. Jones, what if I just leave it like this? If I just leave it like this, will you count this right? Well, here's the problem with this. If you're taking, let's say you're taking the SAT or a college entrance exam, and this question's on it, but it's in the multiple choice form. Well, you're not going to find this answer as one of the multiple choice answers, right? You're going to find this answer as the multiple choice answer. And if this is all you know how to do, then you're really going to be stuck. And right now, while we're taking tests on Canvas, if you didn't know how to do this, you might get stuck right there as well. So we want to always make sure we can simplify everything down to its lowest terms. All right, got a third example here. I want you to pause the video and I want you to work this one and come up with your answer. And then I'll go through it real quickly to confirm that you got it right. All right, so pause and do this problem. Okay, so hopefully you did it. You should have set it equal to 0. And then found your A, your B, and your C value, substituted them into the equation. And once you've done the arithmetic, you would have gotten this. -3 plus or minus the square root of -23 over 8. Now, if you've been paying attention, you recognize, hey, this is the square root of a negative number. 23 is not a perfect square, and it doesn't have any perfect square factors. However, it does have that negative in it, which means it's going to be an imaginary number, right? So hopefully you caught that and recognize that, hey, I need to change this into the square root of -1 times the square root of 23, and the square root of -1, of course, is I. And so we see -3/8 plus or minus the square root of 23/8 I. So notice this is in A plus or minus BI form. It is in a complex number form. So this particular quadratic has imaginary roots. It has 2 of them. It has 2 imaginary roots, which we know means it's not going to cross the x-axis. It's either going to be above the x-axis, or in some cases it could be reflected and open down and be below. But because this one has a positive A value, we know it is opening up, so it has been shifted up and doesn't cross the x-axis at all, but the roots are imaginary. So the quadratic formula will find real roots. It will also find imaginary or complex roots. So sometimes we use different terminology. Sometimes we'll look at that and say, oh, those are imaginary roots. Sometimes people get a little more technical and they will say they are complex roots, non-real complex roots. But just understand, if we, technically that's a complex number. It's an A plus or minus BI number, so it's a complex number. And it's, it indicates that we're using the imaginary unit as part of the number, and it's an imaginary root. All right, let's talk about the discriminant. In fact, I'm going to go back a moment. Remember when we were doing this part, the b squared minus 4ac, and we got this number -23? And we've done that on the other 2 examples as well. Well, that number, that part right there, which in the last example was that negative 23, that is called the discriminant. So we mentioned this at the beginning as one of our learning goals. So you definitely want to know what the discriminant is. The discriminant is this value right here, calculated by b squared minus 4ac. It is a very useful number to find, an amount to find as you're working with a quadratic equation. Here's the bottom line of this. If you're trying to solve one of these problems, you're going to have to calculate that amount because you're going to put in A, B, and C. And so you're going to have to calculate how much b squared minus 4ac is, okay? You're going to be doing the work anyway. Since you're going to go ahead and do the work anyway, you might as well be able to cash in on the work, right? So the smart money says, hey, since I'm going to go ahead and calculate this anyway, I'll happily take a little bit of information, a little bit of insight. You know, it's like the little secret clue. If you know how to read it, it tells you extra information. And what the discriminant will tell you is it will tell you how many roots a particular equation is going to have. And it will also tell you the type of roots that the quadratic equation is going to have. You know, and type of roots may be real roots, the ones where, hey, the parabola crosses the x-axis and we see those two places, or maybe the vertex is sitting on the x-axis and then we see the one root, there's the number, and there's the type. They're real. Or like the last question, the negative 23, we see that they're imaginary roots, and so we know that the parabola doesn't ever touch the x-axis, and they're imaginary or complex roots. So the discriminant will tell me that. How does it tell me that? Real easily, it's based on the value of this number. And in fact, I don't even have to know the exact number. All I need to know is that amount 0? Is it less than 0, i.e. a negative number, or is it greater than 0, i.e. a positive number? So I just want to know, hey, is that amount positive? Is it 0 or is it negative? So if I know which of those three things the discriminant, which category the discriminant falls into, positive, 0, or negative, then I can then know how many roots it's going to have and what type of roots they are. So this is how we tell. Okay, if the discriminant is greater than 0, which is another way of saying a positive number, then the quadratic equation, the parabola is going to cross the x-axis. The quadratic equation is going to have two real roots or real solutions. There's going to be two of them, and they are real numbers. They are going to be real numbers, and we can see them on the graph. They are real solutions. And we say distinct because over here, when the parabola does this, we only see one distinct, i.e. one different root. Okay, if we were to factor that, sometimes we might get something like x, x squared, or x minus 1 squared. When it's x minus 1 times x minus 1, the same root is repeated, but that's just one distinct root, even though it's been repeated. We'll talk more about repeated roots in later lessons. So if b squared minus 4ac is a positive number, there are two real roots. If it equals 0, if b squared minus 4ac is exactly 0, then there's only going to be one real root or one real solution. And then finally, if b squared minus 4ac is less than 0, i.e. a negative number, that's when we're going to have the two complex roots. Okay, so you see it's very wordy here, two distinct non-real complex solutions, which is just another way of saying, hey, it's two imaginary roots, two imaginary solutions. Non-real complex means imaginary roots or complex number roots, okay? Remember that, just like with the quadratic formula, that when we are, if we're just evaluating b squared minus 4ac, we have to make sure our a, b, and c are coming from the equation written in standard form, ax squared plus bx plus c. But if you're using the quadratic formula, you'll already have set the equation equal to 0 and you'll be doing that. But that's the only time that works is when it's in that form. So just an important reminder about that. Okay, so let's practice a little bit. So I've got this equation, x squared plus 36 equals 12x. If I asked you, tell me how many roots it has and what type are they? Can we do that? Well, we can using the discriminant. As we just talked about, this is not in standard form yet. It needs to be set equal to 0. So I would need to subtract that 12x from both sides. But as soon as I do that, I subtract the 12x from both sides. And now I got x squared minus 12x plus 36. Now it is in standard form. My a, of course, is 1. My b is negative 12. My c is 36. So if I want to use b squared minus 4ac, I can do that. Plug in the negative 12 here. Plug in the 1 for a. Plug in the 36 for c. And there I go. And of course, I know a negative 12 squared is 144. I know that 4 times 1 is 4, and 4 times 36 is also 144. So that becomes 144 minus 144, which is 0. And we learned just a minute ago from our little chart that when b squared minus 4ac, when the discriminant is exactly 0, neither positive nor negative, then there is only going to be one real root. Okay, it's that easy. Change one number, so change from 36 to 30 here. Again, I have to set the equation equal to 0. So I'd subtract the 12x, and now I know my a is 1, my b is negative 12, and this time my c is 30. So I plug those in again to the discriminant, b squared minus 4ac. Again, negative 12 squared is 144. 4 times 1 is 4, but 4 times 30 is only 120. So this time when I subtract 144 minus 120, I get 24. Well, that's not 0. 24 is a positive number. Positive number, we know what that means. When the discriminant's a positive number, when it's greater than 0, that means there are 2 real roots. Okay? So I use these two equations up here that were almost the same, 30 in this one, 36 in the last one, because I want you to realize something that's very important for you to realize. Look at these 3 functions that I have graphed here. This one in blue, we're calling it f. This one in red, we're calling it g. And this one in green, we're calling it h. Look at the functions. X squared minus 6x plus 7. X squared minus 6x plus 9. And then the x squared minus 6x plus 11. So in these, they all 3 look like they're almost the same. Of course, the only thing that's different about them are the c values here. And you would think, oh, that's not going to make a lot of difference. It makes a big difference in the number of roots and the type of roots. Notice the blue has 2 roots and they are real roots. Notice the red only has the 1 root at the vertex and it's real. But the green equation doesn't have any real roots. Its roots are complex numbers. Sometimes students think they can tell just by looking at a standard form equation if it's going to have real or imaginary roots or how many. Folks, you really can't tell. You can see these 3 are very similar, okay? And you don't know enough just by looking at the equations for you to make that determination. So make sure you're checking the discriminant, that you are, making sure you know what you're encountering there, so that you don't run into an issue. All right. All right. Finally, I've got something I need you to look up. It's going to be in your textbook and it's on page 178 and it's up there near the top. They give you 2 formulas up there near the top of the book. And I'm not going to tell you what they are right now. I want you to go look them up in your book and I want you to write them down in your notes. One is for when an object is dropped off of a building. When an object is dropped off of a building or from my hand, in any kind of situation where the object is just let go in the air at some height. Doesn't matter if it's off the highest skyscraper in downtown Dallas, or if I'm just dropping it here sitting at my desk and I drop something. The effect on that thing is going to be a quadratic equation or quadratic function type effect, okay? And there's a formula for it, and it all has to do with the effects of gravity and, being here on Earth. That's different slightly from if I throw an object, if I throw a ball or I throw something at somebody, Again, the object is going to take a quadratic path, but the equation that we use is different because we have to account for not just the effects of gravity at that point, but we also have to account for the amount of force that is placed into the object when it is thrown or launched or anything like that. So make sure you look up those two formulas. You're going to use them, and make sure you have the quadratic formula memorized. Okay, the opposite of b plus or minus square root of b squared minus 4ac all over 2a. All right, so I want to show you one final problem here. It's a word problem because I know y'all hate word problems. Some of you just really, you'll just skip a problem rather than do it. But I want you to see how easy it is, and it's using one of those two formulas that I talked to you about. So in this, it says an athlete on a track team throws a shot put. You've seen some track athletes probably do this in the past. You may have done it yourself. So it says the height y of the shot put. So, you know, if you've ever seen an athlete do a shot put, they put it up here under their chin and they twirl around and then they throw it. They throw that metal round ball, that shot, and they push it up into the air, and it goes up in the air and then it comes down and it lands on the ground. So it says the height of the shot put, so how high it is up in the air after t number of seconds after it's been thrown, is modeled by this equation, and they give us the equation in the question. They also tell us that the horizontal distance between, or the horizontal distance x between the athlete and where the shot put lands is modeled by this equation. So when we talk about horizontal distance, we're talking about the athlete stands here, the athlete throws the shot put, you know, travels this path, but we want to measure this distance, the measuring it on the ground. That's what the judges would do when they measured from where the athlete's standing to where the shot put lands. We're measuring this horizontal distance. So that is calculated with this equation. So they give us two equations that we're going to use. And then they ask us, to the nearest foot, how far does the shot put land from the athlete? So we're going to set the height of the equation to 0. We're going to set it equal to 0 here. So set the equation equal to 0, and now I want to solve it. So I'm going to use the quadratic formula. I'm going to use -16. I'm going to use 24 6/10, and I'm going to use 6 5/10. I'm going to plug those into the equation. So I'm going to, you know, I'm not going to spend time doing the arithmetic for you here, but you would probably grab your calculator and plug some of those numbers in, take the 24 6/10 and square it. Takes -4 times -16 times 6.5, and you would take 2 times -16. And so when we do that arithmetic, we come up with this number, of course, the -24, the -32, and then we get the 1,021 1600ths. Take the square root of 1,021 1600ths, and you get approximately 31 9600ths. Now, remember, this is two answers. So I want to, you know, I'm trying to get a, you know, time, and then I'm going to try to get a distance. So I need to get this down to an actual answer that I can, you know, work with and plug in to that second equation. So I'm going to do -24 minus 31 9600ths divided by -32. And then I'm going to do -24 plus 31 9600ths, all divided by -32. And so when I do that, the -24 minus the 31 9600ths, I get this, -56 5600ths. But remember, I'm dividing it by a -32. So a negative divided by a negative is a positive, and it comes out to be approximately 1 7700ths of a second. So 1.77 seconds. Over here, the other one, -24 plus the 31 9600ths, I get this, 7.36, 7 3600ths, divided by -32, it comes out to be a -0.23, a -2300ths of a second. Well, all of you are smart enough to know that time travel, while it would be really cool, is not possible. So we cannot go backwards in time. We're not measuring before the guy throws or before the athlete throws. We want to measure from the time they the athlete throws until it lands. So this answer is not possible. It's not a useful answer in this problem, so it needs to be discarded. That only leaves one answer. That's this one right here. And so that is our answer. It's going to take 1.77 or 1 and 77 hundredths of a second after it's released before it lands and hits the ground. So now I take the second equation they gave me, this 29 and 3/10 t, and I'm going to put in my 1 and 77 hundredths into it, and now just multiply them together. And I come up with 51 and 86 hundredths. So I know that the shot put traveled about 51 and 86 hundredths feet. Now, if you remember in the question, it said to the nearest foot. So if I was going to round that to the nearest foot, I would say it traveled about 52 feet. Okay, so there we go. And that, folks, is the end of the lesson. Okay, so I hope you enjoyed that. And, you know, this is the point where the lesson's over, and most people, you know, movie's over, you start to get up and leave right as the credits are rolling. Now, if you're one of those people that watches a Marvel movie and you know that, hey, Marvel movies, there's always something cool that's going to happen after the credits, a little cool little thing. But if you're one of those people who leaves anyway, then you should go ahead and stop the video right now, because you do not want to see the secret bonus content. But if you're the person that stays, waits through all the credits, and then gets to see the bonus content, then this is just for you. So again, trying to add a little levity here. I do want to show you something. And seriously, folks, if you're not all that interested, you can go ahead and stop the video. You've learned the lesson, we're done. But I do think that as pre-AP, as honors, as GT Algebra 2 students, as the best of the best, the smartest of the smartest, the hardest working of the hardest working students, you ought to know that the quadratic formula is not some magical formula that somebody just sat around and said, hey, let's make up this formula and we'll say that it gives us the answers. It's not a magical formula. It was actually derived using a method that you already know, and that is the completing the square method. So if you want to stick around, I'm going to show you how we come up with it. I'm going to try to do this real fast. This is not something that you're going to be tested over. It's not something you have to know or have memorized. I just think you ought to know this is where it comes from. So here we go. So let's walk through an equation just real quick using numbers. This is, you know, doing the completing the square thing that we learned. I'm going to use those exact same 6 steps that we learned. So I've got the A value, the B value, you know, the C value, got it set equal to 0. So we're going to do the whole thing of X's on one side, constants on the other. You know, the thing about, hey, A value has to be 1, so I got to divide all the terms through by 3. So now I've divided all the terms by 3. I've got the X's on one side, I've got the constant on the other because I subtracted the 1/3 from both sides. Then I'm going to take the B value, which is the 5/3, I'm going to divide by 2. And when I divide by 2, you know, divided by 2, 3 times 2 is 6, I get 5/6. And then I take that number and I square it. That's the, you know, the 5/3 divided by 2, and 3 times 2 is 6, and I square it, and I get 25/36. And on the other side of the equation, I add the same thing, b divided by 2 squared, b divided by 2 squared. So this is the completing the square thing that we learned how to do. We already know it factors into the binomial. Over here, I need to put those two together so I get a common denominator of 36, subtract, you know, I got to multiply by 13, I got to multiply up here to get the common denominator. I'm sorry, I said 13. You got to multiply by 12, and I multiply up here by 12. And so I get 12 over 36, and 25 minus 12 is 13. Okay. Take the square root of both sides, add in the plus or minus, and then you're going to subtract the 5/6. And so I get negative 5/6 plus or minus square root of 13 over 6. Now at this point, you know, I have this common denominator of 6. So I'm able to combine the numerators, -5 plus or minus square root of 13 all over 6. So this is something we've learned how to do. Now, we do the same thing with a quadratic equation in standard form, ax squared plus bx plus c, but we just leave the letters, okay? So just like we did over here on this side, I divided everything by 3, so here I divide everything by a. Just like we did over here, we get the x's on one side and the constants on the other. You know, we're doing steps 1 and 2. Steps 3 and 4, we take the b value, which is the b over a, we divide by 2, which is, you know, here b over a divided by 2. So the 2a down here, just like over here, the 2 times 3 made the 6. And then we take b over 2a and we square it. And since we added it to one side, we got to add it to the other. You know, the box on this side, the box on this side, add the same thing to both sides to keep the equation balanced. Okay. Now, over on this side, you know, I got a and I got 2a, but remember this is being squared. So this becomes b squared. 2 squared is 4, a is squared, so this becomes 4a squared. Now, in order to subtract fractions, you know you have to have a common denominator, right? So on this side, I have a 4a squared, but in this fraction, I just have an a. To make this denominator match this one, I need to multiply by 4a. 4a times a would be 4a squared. And then I also have to multiply the numerator by 4a, so this becomes 4ac, while this one becomes 4a squared. Now I have this common denominator of b squared, I'm sorry, of 4a squared on both sides. So I can put the numerators together, the b squared, and remember we multiplied that by 4a, and that makes the 4ac. So how do I get rid of the square? I take the square root of both sides. I got to put in the plus or minus, and you see this is looking a whole lot like the equation that we're used to. So when I take the square root of the numerator, it becomes plus or minus the square root of b squared minus 4ac. For the denominator, I know the square root of 4 is 2. I know the square root of a squared is a. The square root and the square cancel, and it's a, and so that denominator becomes 2a. So now I've got this over here, right? I subtract it from both sides. Now it becomes negative b, or the opposite of b, over 2a plus or minus the square root of b squared minus 4ac all over 2a. These two are common denominators, which means I can put all this in the numerator together. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's how you get the quadratic formula. You're welcome. Okay, why are you still here? The movie's over. Credits are done. The cool bonus content, it's over with. We're done. Y'all have a great night. Bye.